Okay, so last Tuesday we mainly discussed about this theorem, although not fully, but the last three of these items, right? And so we are mainly discussing about the situation where regardless of any given B vector here, we can guarantee that we always have a solution, right? And then what kind of situation is it, and what conditions should we satisfy in our coefficient matrix? So the main conclusion was every row in our matrix A, so yeah, except for the last coefficient, except for the last constant values, or that last column, up to this part, we should have a pivot in every row, right? So that was our conclusion. So in that case, yeah, regardless of whatever values on the last column, which corresponds to our constant values on the right-hand side of these equations. So yeah, regardless of any values, so these will not influence the patterns of the echelon form and their pivot positions in this left part that contains the coefficient in our linear system. Okay, and then now we will switch the gear a little bit and then discuss about the matrix multiplication and their different perspectives of understanding it. So yeah. So let's look at this example. So this is the vector equation that we saw, right? So in this case, we have three equations and three unknowns, and three equations will be these one, right? So these three are our three equations, right? And then this is a vector equation 4, which is composed of one single equation, but we now have these three vectors, and then the last vector on the right hand side. And then this problem, we studied that this problem can be viewed as finding a suitable linear combination coefficient that creates the three-dimensional parallelogram by using these three given vectors, by stretching or shrinking down the length of these vectors so that the vertex of this parallelogram to be the same as this B vector, right? So that was the interpretation of this vector equation, right? So yeah, so that was what we studied so far. And then now we will look at this linear combination of these three vectors again, and then we will form this as a single multiplication. Okay, so yeah, initially in our linear system, it had, so let's just count the number of multiplications and additions that we have to do in our linear system. So in this case, the first equation was originally like this. 3 equals 66, and then and so on, right? And so we have to multiply, like 3 times with the 60 times x1 and 5.5 times x2 and so on. So we have like 3 additions, 3 multiplication and 2 addition, right? So 3 multiplication and 2 addition, right? And then we should satisfy this this equation to be the same as 66, right? But in terms of the number of multiplication and addition, this is that count. And then we have 3 equations in this linear system, right? And thus we will have exact same number of multiplication and addition 3 times, right? Because we have 3 equations. But if we have a more equation, these numbers will increase, right? Yeah. So far it is obvious. But when looking at this vector equation and focusing on this left-hand side, although the vector contains multiple numbers, still, we can view this as a single equation between this constant vector and x1, right? because in our vector equation, we are given this a single vector, and then if x1 was 2, and then we are stretching out or extending the length of this vector, right, by a single operation, right? And so, yeah, it can be viewed as still 3 multiplication and 2 addition, right? But since we have a single equation, there are no more equations to do the multiplication or additions, right? So effectively, it is from this number times the number of equations, right? Because that was this number 3, right? And then now we reduced the total number of multiplication and additions, yeah, by this amount, right? So that way we can view this problem in a simpler form, right? So it's not just about reducing the number of multiplication or addition. It's more about our intuition of viewing this linear system. So previously, we had to think about all the different or multiple equations, right? But in this case, we can now view it as a single equation, right, that contains these number of multiplication and addition. And then now we will further reduce this number of multiplication and addition that we, in terms of how we understand this left-hand side in our linear system. So that is quite simple. So in this case, let me just write it in this form. Let me see. Yeah, so we have this form already. So this part, or this matrix times this vector, okay, so this will actually form the exact same representation that we are given on the left hand side, okay. So let's just prove it or verify it just mechanically. So let's see, I will just move it to here. So yeah, so the first typical way of viewing this matrix and vector multiplication is based on some inner product, which is this row vector times this column vector. You guys know the inner product, right? And so in this case, 60 times x1 plus 5.5 times x2 plus x3, right? So that is the result of the inner product with the first row here and this column on the right. And then the next one will be to multiply this row and this column, right? And so that will result in x1 0 times x3, right? And then 55 x1 6.0 x2 plus 1 times x3, right? So although it looks a little bit big, but this one is scalar and scalar and scalar. So that way we formed just one single vector, right? And then we have to equate, or we have to make it equal to the given right-hand side. For example, if our right-hand side was a 66, 74, 78, this one will be our equation, right? And then, yeah, we have to make it equal for each element in our vector, right? So that way we can see that this one is exactly the same as the original linear system that we have. And then this linear system can be viewed as this linear combinations of the columns that contains our coefficient values, right? And so the point is this part, okay, this part can be further simplified into this form, okay. So let's view or understand this form, which can be represented as matrix A times the vector x, okay. So in this case, we can now view this one as this guy and this guy, this guy, we have a 3 columns, right? And then we have this linear combination coefficient that are multiplied with the first column, and then the second one, and the third one. Okay, so that way we can view matrix and vector multiplication as a linear combination of these 3 columns on the left matrix, and then using these scalar values on the right in our vector as a linear combination coefficient. Okay, so that's how we can view this matrix vector multiplication. Okay, so this A matrix is represented as these 3 columns in this case. So these are vectors, right? Because they are bold-faced, and then x1, x2, x3 are linear combination coefficients. And then it can be represented as just a simple linear combination of these columns, right? So this is what we already studied, right? Okay, so so now looking at this example, when computing this matrix vector multiplication, we would just do this guy times this, or inner product between these, and so on, right? But in this case, we can view this as a linear combination of these 3 columns, where we have these 3 columns, and then those 1 to 3 are associated as a linear combination coefficient. Okay. So far, yeah, it is quite easy, and then it is just a slight or small extension of what we learned already. But what if we view this matrix vector multiplication, where we had a matrix on the left and the vector or column vector on the right, but let's generalize it into just a any matrix and matrix multiplication. Okay. So when doing this matrix multiplication, first of all, the size. What is the size of this matrix multiplication? So we have 3 by 3, right? So and then we have 3 by 2, right? So the resulting matrix size will have 3 by 2 because these two numbers will cancel out, right? And then what would be the typical way of our matrix multiplication? It will be like this guy and this guy, right? And then computing the inner product. So let me just write it first in terms of it's a result size of the resulting matrix, and then those two guys will be used to compute the inner product, and then that will fill out this single scalar value, right? And then let's see, this guy and this guy, the same guy, will form this guy, right? And then this guy and this guy will form what? This guy, right? So far so good, right? So this is what we already know, but we can also understand this matrix multiplication in terms of the linear combinations of the columns that we just studied. So, so this is a resulting matrix in terms of their size, and then let's first look at this first column in the resulting matrix. Okay, so this part. So this part can be viewed as the linear combination of the columns on the left matrix by using the linear combination coefficient of these values. Okay, so let's look at that. So let's look at y. So this guy times this guy will form this guy, and this guy times this guy, and this guy, and this guy times this guy, right? And then if we view them as a column by column, so we have these 3 columns, and then these 3 columns, and using these 3 as a linear combination coefficient, and then they will form this part. Okay, And then what about this value? What about these values? So these values will form the second row in our second column in our resulting matrix, and they will use the same column vectors and using a different linear combination coefficient. Okay. Okay, so in short, when doing the matrix multiplication, when viewing it as a in a column-wise form, then the first column of the resulting matrix can be computed as a linear combination of these columns on the left matrix. Okay, and then using these three as a linear combination coefficient. And what are these three? So these three are the first column on the right matrix. Okay. And then for the second column that we have in the resulting matrix, that will be formed as a linear combination of these three, still using the same vector, but using different linear combination coefficient. Okay? So, looking at this, we can kind of understand or think about their interesting properties about the columns in our resulting matrix. So, suppose we are given like these 4 columns in our matrix, and then let's think about the matrix multiplied on the right, and then what should be the dimension of each column in our matrix. So for each column on the right matrix, that works as a linear combination coefficient associated with each of our vectors, each of our column vectors given on the left matrix, and thus we should have 4 different values in each column on the right matrix, because we need 4 different linear combination coefficients that will be multiplied by these 4 different vectors, right? And then suppose that is 1, 2, 3, 4, and then the first column in our resulting matrix will be the linear combination of these 4 by using the coefficient as 1, 2, 3, 4. Okay, and then let's move on to the second column, this guy. Okay, on this guy on the right matrix, and then how many numbers do we have? Still 4 different numbers should be given, because we need a 4 different linear combination coefficient. But let's suppose that as 4, 3, 2, 1. Okay, so that will form this guy will work as a new linear combination coefficient to create another column on the resulting matrix. So this guy. Okay, but they are still using the same column vectors for their linear combinations that are given on the left matrix. And then if we are given the third vector, and then that will also work as a different linear combination coefficient, and then that will form the third matrix, the third column in the resulting matrix. And then in that case, let me ask the question here. So these 3 resulting vectors, these 3 vectors in the resulting matrix after this multiplication, okay? Is it possible that each of these vectors is outside of the span of these green vectors that we are given? So here the point is, these 3 vectors should be represented as a all linear combination of these same 4 vectors, but using different linear combination coefficients, right? So in that case, those 3 vectors should be inside of the span of these green vectors, right? 표정이 이렇게 안 좋지. 자, 내가 하여튼 영어가 딸려서 한글로 좀 설명을 다시 해줄게요. 되게 하여튼 중요한 거라 참 되게 중요해요. 되게. 자, 일단 이게 자, 이게 일단 매트릭스 벡터일 때 매트릭스 왼쪽에 있는 걸 컬럼, 그죠? 컬럼들의 리니어 컨비네이션으로 결과가 하여튼 나타난다. 그거까지는 이해했죠? 그래서 매트릭스와 벡터의 곱배에서는 저걸 저렇게 볼 수 있다. 거기까지는 오케이? 그죠? 자, 그러면 이쪽에 이제 매트릭스와 이쪽에 이제 벡터가 주어지면 이게 어떻게 돼? 벡터가 아니라 이제 일반적인 매트릭스가 주어지면 어떻게 되느냐? 이게 지금 우리가 좀 이거 우리가 바로 전에 했던 걸 확장을 하고 싶은 거예요. 그러면 여기서 나타나는 매트릭스의 사이즈는 기본적으로 여기 아까 얘기했던 3x3, 3x2면 이 나오는 결국 매트릭스의 컬럼은 몇 개죠? 컬럼은 바로 이 오른쪽 매트릭스에 주어진 이 컬럼의 개수랑 똑같아요. 그렇죠? 3x3, 3x2 그러면 저 2가 리저팅 매트릭스의 컬럼 개수를 결정을 해요. 그죠? 그래서 우리는 이 매트릭스 멀티플리케이션 일단은 다 컬럼들의 뭔가로 보자는 거예요. 그러면 여기서 만들어지는 first 컬럼, 그러니까 첫 번째 컬럼은 이제 어떻게 되느냐? 첫 번째 컬럼은 어떻게 되느냐 하면 여기서 주어진 매트릭스를 역시 컬럼들만으로 봐요. 컬럼들만으로 보고 요 놈들을 리니어 컨비네이션 코에피션트로 써서 요 첫 번째 컬럼을 만들고 그 다음엔 여기에 주어진 요 두 번째 컬럼 다시 한번 얘기하지만 여기서 이 오른쪽 매트릭스에서의 컬럼 개수가 곧 우리의 만들어지는 매트릭스의 컬럼 개수랑 똑같고 여기서 만들어진 첫 번째 그러니까 매트릭스에서의 첫 번째 컬럼은 바로 이 세 개의 리니어 컨비네이션. 근데 그 리니어 컨비네이션 코에피션트 얘네들로 썼고 그 다음에 두 번째 컬럼을 만들 때는 동일한 조금 지저분해져서 그렇지만 요 놈들 동일한 애들을 이제는 얘들의 리니어 컨비네이션 코에피션트를 써서 이 두 번째 컬럼을 만든다가 돼요. 왜 그러느냐? 그냥 해보면 되는데 이제 그러니까 요거 해서 요거 만들어지죠. 요거 해서 요거 해서 요거 만들어지죠. 그렇죠? 그러니까 얘네들 만들 때는 물론 왼쪽에 있는 건 다 쓰였어요. 근데 오른쪽에 있는 거는 누구만 쓰였느냐? 바로 얘만 쓰였죠. 그렇죠? 이렇게 돼요. 그러니까 결과적으로 만들어지는 매트릭스의 컬럼들은 이 두 번째 매트릭스로 보면 여기서 첫 번째만이 관여를 해갖고 여기에 첫 번째 애들을 만든다는 뜻이고 여기에 있는 두 번째 얘가 관여했을 때 얘가 관여해서 이 두 번째 컬럼을 만들어낸다는 뜻이에요. 그러니까 이걸 따로 볼 수가 있고 이것들 어떻게 보면 이렇게 쭉 이렇게 이어붙인 거라고 볼 수가 있어요. 그래서 공통의 컬럼 벡터들을 가지고 오른쪽에 주어진 매트릭스의 그 각 컬럼별로 그 컬럼 하나하나가 이제 그 서로 다른 리니어 컨비네이션 코에피션트를 사용을 해서 그러니까 리니어 컨비네이션 된 최종적인 컬럼들을 이렇게 그 리니어 컨비네이션 코에피션트를 다르게 써서 이렇게 만들어낸 것들을 옆으로 쭈르륵 붙인 게 그게 우리의 결과적인 매트릭스다 이거. 질문. Okay, so yeah. In summary, on the left matrix, it provides the common ingredient vector to be used as a linear for the linear combination, right? And then in the right matrix, each column will work as a linear combination coefficient that will form the linear combination vector by using these common vectors. And then that will form the first one, and this set of linear combination coefficients will form the second column in the resulting matrix. Okay, so yeah, back to my question just before before explaining it in Korean. Each column in the resulting matrix should be inside of the span of these three vectors, right? Because although we are using different linear combination coefficient, but we will use the same ingredient vector that are given on the left matrix, right? So those columns cannot be outside of the span of these three vectors, right? Okay, yep. And then we can view it as a row combinations as well. Let's think about, so in this case, we have A times X, right? And then, this is a vector, and this is matrix. And then we can view it as X transpose, A transpose. Do you guys know what the transpose is? Did I explain it already or not? Transpose. 1, 2, 3, 4. What is the transpose of it? So we just draw this a diagonal line and then flip it, right? And then, so in the diagonal, the elements will be the same. And then, this guy, moves that part, like so. Then this guy, is moved here. True. So this is our matrix transpose. Okay. 이거 배우지 않았어요? 고등학교 때? 네? 고등학교 때 안 배웠어요? 그게 앞으로 빠진다는 게 아니라 여러분들도 안 배웠던 거예요, 그걸? 참 큰일이네. 네, 뭐 트랜스포즈 알겠죠? 대칭, 대각선의 대칭. 그래갖고 매트릭스를 이렇게 180도 돌린다. 그럼 이것도 모르겠네, 이것도. Transpose. So one interesting characteristic of our transpose operation in our matrix is that, so what if we just do the transpose of it? So in this case, so what is the result? Let's see. It doesn't have the result, but 그 회전이동 이런 거 안 배웠어요? 내가 물어봤나 이것도? 회전이동 같은 것도 안 배웠어요? 네? 그럼 평면의 방정식. 평면의 방정식 했어요? 법선 벡터 뭐 이런 거. 그건 했어요? 법선 벡터는 했어요? 그래요. 네. Okay. So let's think about let's just compute this result. So the first entry is 1, 2, 0, and 3, and then 1, 3, and so forth. So it's 3, -2. It's 4. Is it? So the resulting, I just wrote the resulting vector of this matrix vector multiplication. Okay. And then in this case, so we now understand what the transpose is, right? But what if we do the transpose on this vector? And then in that case, we draw still we draw this diagonal line that has the degree of -45 degree, and then we flip it, right? And then it will be 3 and 4, 4. So this column vector will be will become the row vector. 이해요? 네, 여기가 1이었군요. 그러네요. 여기, 네. 이렇게 되죠. Okay, and then we now know how to do the transpose on the vector as a special case of a matrix, right? But when having this matrix vector multiplication or matrix multiplication, what if we do the transpose of it? And then it will be represented as this guy. So we can do the transpose on the vector and the matrix, or other matrices that are part of our product or multiplication. But we just apply the transpose on each of our elements in our product, but also we actually change the direction, or we reverse the order of this multiplication. So that's the one important property of this transpose. So in general, suppose let's think about this A, B, C as a matrix product of these three matrices. Okay, so in this case, it can be represented as this guy. So that means, this process is doing the matrix multiplication first, and then resulting matrix, and then do the transpose, right? And then in this case, we first transpose each of our matrix, and then multiply it in a reverse order, right? And then it's the proof is really tedious. You can just set maybe A as maybe A11, A12, A1 and A1 N and so on, and then you do really tedious writing on these matrix multiplication, and then verify that this guy and this guy is the same. But let me just give an idea in terms of why it should be true in terms of the matrix size. And suppose A is 5 by 3, and then B should be the first. What should be the first number? It should be 3, right? Because those two numbers should match, right? And then what will be the second number? Let's see. Let me give a 4, and then maybe this number should be 4 as well, and then maybe 2. What will be the resulting size of the matrix? 5 by what? 2. That is obvious, right? And then in terms of the size, what will be the size, the transposed matrix? I mean that the size of the transposed matrix, of course, 2 by 5, right? And so in this vector form, if we view it as a matrix, it will be 3 by 1, and then when transposing it, it became 1 by 3, right? Okay, so in this case, let's just verify at least the size of the resulting matrix when doing this this guy. So C transpose, originally C had a 4 by 2, and then C transpose will be 2 by 4, right? And then B transpose will be 4 by 3, right? And then A transpose will be 3 by 5, and so they will be matching properly, and then the resulting matrix size will be 2 by 5, right? Okay, so at least we verified the size is matching if these two equal. If these two are equal. Okay, so back to our form of matrix A times vector X, and then when doing the transpose, we know that the resulting vector, it will be transposed into a row vector, and then when multiplying, when applying the transpose on this product of this matrix, and then that will be changed into X transpose and A transpose. We now understand that, right? Okay, and then let's just write it directly. Write the transpose form. So here we had a 1, 2, 3 as a linear combination coefficient for our column on the left, right? And then this guy will be transposed into this vector, and then it will be placed first, right? And then this matrix will be transposed, and then you guys know what the transpose will be. It will be like we write it as a row 1, 1, 1, and this guy as a 1, 0, negative 1, and 0, 1, 1, right? So that will be our transpose version by just drawing this line and then flip it, right? And so if we view that as a like this kind of column, and then you guys know that it becomes the first row, right? In terms of this flipping kind of pattern. Okay, so that will be this matrix, right? And then, so in this case, if it was the column linear combination of these three columns, and then this vector was the resulting linear combination of these vectors, and then if we flip it, and then we can easily understand that. Yeah, so columns were flipped into row vectors, right? So we have these 3 row vectors, right? And then these values will work as linear combination coefficients of rows, right? I mean, yeah, linear combination coefficients associated with these rows, right? So that is easily understood from this transpose relationship. So we have these 3 ingredient vector or given row vector, and then we have these 3 linear combination coefficients for these row vectors, and then the resulting row vector can be computed. Yeah, really simple. Yeah, so we can do the computation, and then the resulting vector will be still 3, 4, 2, right? And so by using the column combination perspective of a matrix vector multiplication, we can understand this as an easily by just transposing it. And now, in this case, it's a special case of a matrix-matrix multiplication where we have a vector on the left and the matrix on the right, right? Vector and matrix and their multiplication. And in case we have a vector on the left, it always should be a row vector, right? It cannot be a column vector, because if it is column vector here on the left, and then what is the size? Suppose we have a size of a 3 by 1, and then the resulting, this part on the right, it should always have the single row, right? It can extend along the horizontally, but it cannot extend vertically. So that way it cannot form a general fat matrix, right? And so the vector on the left should be row vector. Okay, and then we can also generalize it into a matrix-matrix multiplication by extending this row combination perspective. Okay, so in this case, this was a vector, right? So let's extend it or generalize it into a matrix, right? And then we now have the first row, and then we can now have a second row, right? And then we have initially a single row, or one row on the left, and thus the resulting matrix after doing this multiplication will have a single row. So this number will be the same in terms of a size, but we have 2 rows, right? And then the resulting matrix will also have these 2 rows, right? And then each row on the resulting matrix will be represented as a linear combination of this same row on given on the right matrix, and then using different linear combination coefficients. So when forming this guy, then it will use these 3 numbers as a linear combination coefficient for these 3 vectors, right? Then for the second row, that will use these 3 as a linear combination coefficient of the same 3 row vectors given on the right matrix. Okay. And then there is another perspective of viewing this matrix-matrix multiplication. So so far we studied about how to understand matrix-matrix multiplications in terms of column combinations and the row combinations. And then the last view or perspective of understanding matrix-matrix multiplication is as follows. So let's also start with this special case where we have these 2 vector multiplication, but this one is called, instead of the inner product, this one is called the outer product. And in this case of an outer product, matrix size will be something like 3 by 1 and 1 by 3, or it can even be like we have a 4 here, and then in that case the size will be 1 by 4, right? And then if we view them as just a general matrix, what will be the size of the matrix multiplication? Those 2 numbers matches, right? Those two number match, so the matrix multiplication is can be done, and then the resulting size will be 3 by 4, right? And then what will be the resulting matrix? We can also view them as a column combination or row combination in this case as well. So let's apply the row combination. The column combination first, because that's the first one that we studied. So in this case, how many columns do we have on the left matrix? How many columns? Just one column, right? Just one column. And then how many? How many columns do we have on the right matrix? So in the case of one, so we are considering this 1, 2, 3. No. 1, 1, 1 as the single column, and then 1, 2, 3, 4. Let's consider this. And then again, we have a single column. And then how many columns do we have on the left matrix, the right matrix? We have like 4 columns, right? Although each column should have the same number of linear combination coefficients as the number of columns given on the left matrix. So we have one column only, and thus we have one linear combination coefficient, right? And thus, so this guy works as a linear combination coefficient to form the first column on the resulting matrix. And then this guy is 1, and so we just simply multiply it by 1. So 1, 1, 1. And then this guy, which is our second column on the right matrix, will form the second column, and then the linear combination coefficient is 2, right? And so 2, 2, 2, right? And 3, 3, 3, and 4, 4, 4, right? Okay. So let's verify one interesting characteristic that I mentioned in this case. So what is the span of these vectors? So we have only one vector, and if we consider the span of this one vector, it will be represented as a single line, right? So we have a 1, 1, 1 here, and then the span of this vector will be just a single line, right? And then are these 4 vectors inside of the span of these, right? So it is true, right? So we can also verify that these 4 vectors in the resulting matrix will be inside of the span of the vectors given on the left matrix. Okay, and then now let's think about a general case where, so in the previous case, we had only one column vector and the one row vector on the left and right respectively, but in this case, let's just extend it. So we had only one column, and now we have another column. And then we now have 2 columns to be used as a linear combination, right? And then in each column in our matrix, we need 2 values this time, because we have 2 ingredient vectors, right? 2 given vectors, and thus 2 linear combination coefficient, right? Okay, and then this is a column combination perspective, but let me just slightly manipulate this guy into this form. So we have this guy, and this guy was the linear combination coefficient associated with the first column vector, right? And this guy came from here. And then, in the resulting matrix of these, the first column will be the linear combination of these 2 vectors, right? But we can first form this matrix by only using this guy and this guy. And we can form this outer product with this vector and this vector, so that we form this guy. And then in this case, we have the second column vector here, right? And then we bring this guy here, okay? And then what is this matrix? So this matrix will still form the exact same size of the resulting matrix. So resulting matrix size will be 3 by 2, 2 by 3, and then it will be 3 by 3, and then this guy will form also the 3 by 3 matrix, but the first one is only using this vector and the linear combination coefficient of this guy, right? That vector will be placed here. And then what about this guy? This guy is only using the second column vector that we are given here, right? And then their linear combination coefficient here. And so, yeah, this guy will be multiplied over here, and 1 minus 1, 1 here. It is multiplied by 4, right? And so it will form this vector, right? And then after doing so, let's just add them together, and then eventually, yeah, we have this guy times this, and that will result in this matrix, this vector, and this guy, okay, this guy times this guy, that will result in this matrix. And then these two, when they are added together, the resulting matrix will have, yeah, this yellow one and this red one will be added together, and then finally form our linear combination of these two matrices, two vectors, right, to form the first column. Okay, and so in summary, suppose we have these two matrix multiplication, okay, and then we now have 4 columns in the left matrix, and then how many row vectors do we have? So we have a freedom to choose this size. So we can have maybe 100 columns on the right matrix, but in terms of rows, the number of rows should match the number of linear combination coefficients that are given here, right? So we should have 4 numbers, right? And then in that case, we can view it in this form, right? And then let's enumerate it. 1, 2, 3, 4, and 1, 2, 3, 4. Okay, and then yeah, let me give just a size, maybe 5 by 4 and 4 by 6. Okay, and then this guy and this guy. So these two are all the first one. Okay, so this came from here and this came from here. Okay, let's see. Okay, so in this case, this outer product will form what? What is the size? 5 by 1 and 1 by 6, right? And thus it will form this big matrix of 5 by 6, right? And then you guys know, yeah, you guys understand that it's all scalar multiple of this first vector, just like we had a scalar multiple of this vector by using a different multiplication factor, right? Okay, and then these are added together with the second vector here and these second vector, and these are the second one coming from here and coming from here, and that will form also this big matrix, right, of a 5 by 6. And then again, how we understand it is as follows. So we have the first vector here and the first vector. So they are added together eventually to form a single 5 by 6 matrix, right? In that case, so this guy will be containing this guy times this scalar multiple, right, for our linear combination. And this guy is what? This guy times this guy, right? And then that will form this guy, right? And that way, that will also add to our linear combination. And then as we add add them together, like how many matrices like this do we have? 4, right? Because we have 4 columns and rows. Okay, good. And then altogether, when we adding them together, and then we will finally have the exact same linear combinations of these columns by using these linear combination coefficients and these and so on, right? Okay, so this one is called a sum of rank 1 outer product. Rank 1 outer product. And do you guys know the outer product and what that is? The meaning of it? So you guys know inner product, right? Inner product. 내적. 내적이라는 거 알죠? 내적. 그 다음에 이거는 외적이라고 해요. 외적. 적은 아마 뭐 곱한다 이런 뜻인 것 같고, inner, 뭐 안으로 해갖고 내적, 그리고 이건 바깥으로 그래서 외적이라고 불러요. 이제 so inner product is basically shrinking many numbers into one. Okay, so we have like these 4 numbers and also 4 numbers, and generate a single number. So that is combining all these 2 sets of 4 numbers into one single number. So that is called the inner product. But in the case of an outer product, it is something like this, right? It's a 3 by 1, 1 by 5, for example. In that case, we have 2 vectors, 2 thin vectors, right? And then it will form really big matrix, 3 by 5, right? And so how many numbers do we have? We have 15 here, right? But originally, how many numbers are participating in this multiplication? Only like 8. So in total, 3 and 5 different numbers, or 2 sets of vectors, each of which has the size as a 3 by 3 and 5, and in total 8 numbers is like expanded into 15 numbers. Okay, so that way, it's expanding our given numbers, and thus we call it as a outer product. And one thing to note is that given these 2 vectors, the size doesn't need to be the same, right? In this case of an outer product, right? Because in this case, the matching number, in order to properly define the matrix multiplication, those 2 numbers will always be 1, because they both of them are vectors, right? Okay, so this is an outer product, and this representation of this this relationship is quite useful, and they are often used in the machine learning and the artificial intelligence, or maybe deep learning and so on, right? And so initial in these tasks, suppose we are given this big number as a matrix. Okay, in this case, what if this matrix was found in this simpler form of these matrix vector multiplication that involves much smaller numbers? Okay, so if we are given these 2 vectors, and then their product of this this outer product, computing this outer product will be really easy. But the more interesting and more difficult problem will be to find out these 2 vectors given this this big matrix. Okay. So if we can find these 2 matrices, these 2 vectors that would have formed this big matrix, and then these results will be really useful in many different applications. Machine learning and artificial intelligence applications. So I cannot give a full explanation about how we can utilize this in different situations, but one interesting kind of application that I'm going to just briefly describe is like a recommender system. So recommender system is basically like, so you watch a particular movie like Die Hard or any kind of action movies, and then maybe Naver Movies or Netflix wants to recommend some some potentially interesting movies to you based on his or her previous like a movie watching histories. Okay, so in that case, we can build up our matrix as like a user by item. Okay, in this case, maybe John has watched the movie of a Die Hard. Sorry for giving really old movies. But I'm not sure if you guys even know this movie or not. But suppose this value is set. We set this value as 1 because this John watched this movie already, and also another movie as maybe Transformer. Okay, so it's a little bit more recent movie. So we set as 1 here. Okay, and then maybe set all zeros, for example. Okay, or these zeros are representing that this guy John didn't watch this movie yet, right? But that doesn't mean that he doesn't like that movie, right? So the fact that he didn't watch that movie does not mean that he doesn't like this movie, right? It may be because he hasn't just found this movie yet, right? And so we can view it as like maybe unknown values or question mark or something like that. Okay, and then okay, so because we are talking about the column combination, let me give an example in terms of a column. So let's just transpose this matrix. Okay, so that we have user here and then item as a movie, right? And then this guy is John, and then maybe this guy is Die Hard, and then maybe Transformer here, right? And then we do not know yet about these values, right? And then suppose this guy was actually a product. It can be represented as these product of these single sets, I mean a pair of single vectors. Okay, so in that case, suppose we found this single vector, which we find here, and then this big matrix, and each column of this big matrix is nothing but a scalar multiple of this single vector, right? So that's how we understood this example. So the single vector and then their scalar multiple is given here, right? And then given this incomplete information where this John watches this movie of a Die Hard and a Transformer and not yet known for any other movies, and then somehow suppose you found this single vector. Okay, so this single vector, and then that single vector was something like Die Hard here and Transformer here, and then maybe some other movie here set as 1, and then this guy is maybe corresponding to maybe Terminator. Okay, suppose you found this vector fully, and then it is forming this big matrix, and then this guy, right? So this guy is just a scalar multiple of this vector, and that will form this vector. And that means if we know the value of 1 here by fully knowing this vector, and then we can basically reconstruct all these unknown or question marks values. So that means even before John has watched the Terminator yet, okay, so we do not know yet, but we will know that he will watch that movie at some time or in the future. So that's how we predict John's preference about the movies, right? And that's how we can kind of do some recommendation. Okay, but what if it's a really special or simple case? So the real kind of problem setting is a little bit more complicated, but so let's consider maybe Jane, and Jane hasn't watched this Terminator maybe not Terminator. Yeah, so it was like a Die Hard, right? And then maybe, yeah, this movie was like Die Hard and the what? Transformer or something like that. Okay, so Jane didn't watch this movie yet. Okay, so these values are set as 0, and then what will be the scalar multiple to form this vector by using the same vector here? What will be the scalar multiple? It should be 0, right? So we know that this vector is setting 1 here as maybe Die Hard and Transformer and Terminator and so on. And then this Jane, we know that the Jane doesn't like the movie, or maybe this movie as 0. And that means, yeah, in terms of a scalar multiple of this vector to form this Jane's vector, okay, so the scalar multiple should be 0. Okay, so that's that way we can also reconstruct this Jane's vector as well. But yeah, this vector, yeah, you can view this vector as like an action movie type of a preference, right? So it's like some guy watched a Transformer and Terminator, but not yet Die Hard. But that vector is actually a scalar multiple of that vector, and that's how we know that he will also watch the other action movie, right? But that doesn't explain this Jane's preference. And here in this case, all the romantic movies are set as 0. So that's the single vector representing the action movie type of a vector. And then what if we have another vector? Another vector, which means here one matrix can be represented as a single product, single sum of one single outer product, but also it can be viewed as like the product of the two outer products, right? And then the first one is like containing the preferences of an action movie, or the watching histories of all the action movies, right? So that is the first vector. And then if we are given the second vector that has all ones corresponding to like romantic movies, okay, and that vector can now be representing this Jane's vector as well. Okay, I tried to explain, yeah, how it works, but yeah, it's okay even if you do not understand about it. But yeah, when you have a chance to study like a recommender system, or more exactly, it's called a collaborative filtering, and this 협업 filtering이라고도 하죠. So this collaborative filtering is just nothing but matrix, like a factorization based on this sum of rank 1 outer products. Okay, that means we initially are given this big matrix, but we try to represent it as some form of a sum of rank 1 outer products. Okay, just like this one, right? And and then this rank 1. So you might be curious about what this rank 1 means, but yeah, we will study it a little later on. We will have a chance to study it in more detail. Okay, so in summary, we studied like perspective of a matrix multiplication as a column combination, or a linear combination of columns and the rows, right? And also sum of rank 1 outer product. Okay, and then it's 4 different views, but the first view is really simple one. So it's like this guy and this guy will form this one, right? It's all based on the inner product, and then I think you should be you already know about this. Okay, so okay, let's go through this matrix, our lecture slides. Okay, so in this 1.4, although we study much contents about it, but here the title is a matrix equation. So we studied the linear system, and then it's a vector equation form, and then we now learn this matrix equation form, and then it's really simple one, and this is already what we learned. So this guy, if we were given the left hand side as this in our linear system, and then it can be simply be viewed as matrix A times vector X. Okay, so matrix A will contain all the coefficients, and then the vector X will contain our unknown variable, right? That will form the linear combination coefficient, right? And then that is represented by this, right? And then in our vector equation form of maybe x1 times a1 plus x2 times a2 plus x3 times a3, and then that will be equal to the given vector v, which contains all the constant values on the right hand side, right? And then this was our vector equation, and then now this can be viewed as ax equals b as another single equation, right? And then related to that, I just wanted to tell you or try to emphasize that. So starting from all the most basic form of this set of linear equations that contains these many number of multiplication and addition times the number of an equation, right? And then that can be viewed as much smaller number of multiplication and addition from the vector equation. So vector equation will remove this operation, right? And then what about the matrix equation? So matrix equation is really nothing but just representing or rewriting this vector equation form into just this form, just collecting a 1, 2, 3, and then form our matrix A, and then x1, 2, 3, and then form our column vector x, right? So that is called a matrix equation, right? And then in this case, how many additions or multiplications do we need? So we have a single equation, right? So that single equation came from this a single vector equation, but in this single vector equation we had a 3 multiplication and 2 additions, right? But in this case, yeah, it is just a single multiplication, no other addition, right? So that way we can view our entire linear system as just a single multiplication. Okay, although when just writing this matrix multiplication, and then inside of it, it will all involve this multiplication and then addition, right? So the actual computation is really the same, right? It doesn't give real or actual benefits in terms of a computation time, but this is about how we understand or how we view our linear system, okay? So from many multiplication and addition, we cannot understand that as a kind of one single operation. But in this case, now we can view this as a one single operation between this matrix and vector, and that will open up really interesting and new perspectives of how to understand and solve a complicated problems. Okay, so that is really the point, and that kind of perspective is really useful and widely used in many different really complicated problems, such as deep learning, for example, or any other machine learning and artificial intelligence applications. So this is very first kind of starting point. Okay, simplifying the problem and simplifying our perspectives, and that way we can build up much more complicated kind of processes and algorithms based on this simplified building blocks. Okay. So now, we can understand what this matrix equation is, right? It's just nothing but just simplifying our vector equation into this matrix times vector form. So that's it. And then now, in terms of the notation, the capital letters are representing the matrix, and also again this boldface lowercase is representing a vector. Okay. Okay, and yeah, in this vector equation, where or linear combination of these three vectors, yeah, that can be represented as this matrix that combines or that collects all these columns given here, originally from this linear combination of the columns, and then we collect all these three components or the linear combination coefficients to form the column vector on the right, right? Okay. Then this linear system can be represented as this single matrix equation, right? Okay, and then our augmented matrix can also be represented in this form. So given this matrix equation, which is really the simplified form, and then we just matrix A and vector X and B here, and then so we just collect all these columns here, and then bring this right hand side matrix vector B, and then this is like a simple form of our augmented matrix. And then now, let's just finish up or complete this theorem 4. Okay, so we understood the last three, but we skipped or omitted the first one, and the first one is really easy one. So this matrix equation should have a solution for any given vector B, right? So this matrix equation, now we understand this matrix equation is equivalent to the vector equation or the originally given linear system, right? It's all the same equation, and if this matrix equation has a solution for any given vector B, and then it means that regardless of even before seeing what particular B is given, we can guarantee that the solution will exist. And then we will skip this proof of this theorem. So I don't think it is really important personally. So you can, as long as you had a high-level understanding or intuitive understanding, at least by following my lecture that we had here, and then that's enough. Okay, so you don't need to understand this proof formally. Okay. Okay, so let me stop here. Then, we'll meet again next Tuesday. And then, don't forget to do your homework and submit it before the deadline. Okay, thank you very much.
얘를 X를 아까 밑에 보니까 이렇게 위에서 아래로 쪼개가지고
네.
실제로 얘 이렇게 계산할 때는 지금 이렇게 하고 이렇게 하고 이렇게 하고 이렇게 하는 거 맞나요?
지금 요거 해서 요거 생성하죠. 그다음 요거 해서 요거 생성하죠, 그죠? 네. 그러니까 요거는 지금 보면 이 전체를 다 썼고 지금 얘만 쓴 거죠. 그렇죠? 그래서 이 첫 번째를 만들어냈어요. 그 다음에 이 두 번째는 지금 역시 똑같은 거 이거 하고 이거 하죠. 그래서 얘 생성하고, 그죠? 얘하고 또 얘 해서 얘를 생성하고. 즉 이 두 번째 컬럼은 이 전체를 다 썼되 요것만 썼어요. 요것만. 그렇죠? 즉 그 말은 이거에다가 이거를 곱하면 첫 번째 벡터를 곱하면 이놈이 나오고 두 번째 벡터를 곱하면 이놈이 나온다는 거예요. 그러면 얘는 이제 얘에서의 어떤 요 컬럼들과 요 놈들을 이제 리니어 커뮤니케이션 코에피션트를 써서 만든 벡터고, 또 이거는 두 번째 벡터, 이 통으로 봤을 때 이 두 번째 벡터는 역시 여기서 이제 동일한 벡터를 써서 리니어 커뮤니케이션을 요 개수를 사용을 해서 요거를 만들어내는 거예요.
그러면 그 얘랑 지금 X는 그냥 이거 위에 컬럼 벡터만 이렇게 따가지고
네.
1, 2, 3 곱하는 건데
그렇죠. 1, 2, 3. 네. 그리고 이 두 번째 줄은 또 똑같은 벡터를 리니어 커뮤니케이션 컴퓨터를 마이너스 1, 0, 1 써갖고.
그러니까 계산할 때는 이걸 쓰고 지금
네. 네. 계산을 실제로 그렇게 할 수도 있는데 이거를 컬럼별로 그렇게 나타내거나 우리가 그렇게 이해를 할 수가 있다라는 거예요.
그러니까 두 개 다 되는 거예요.
네, 두 개 다 동일하다는 거예요. 네.
중간에 과제에서 그 주석 넣으라고 돼 있더라고요. 주석을
그냥 적당히 그러니까 뭐 이게 뭐 하는 것이다라는 거에 대해서 설명을 뭐 한두 줄씩 넣으면
일일이 다 하나하나예요.
한 줄 한 줄 다 넣을 필요는 없고 좀뭐 중요하다 아니면 의미가 있다 싶은 것들을 뭐 너무 이렇게 좀 뭔가 성의 없이 하면 또 그렇겠지만 또 그거는 뭐 이렇게 좀 요 줄에서는 왜 주석을 안 달았는지 거기서 감점시키고 그러지는 않을 예정이니까 하면서 뭐 그냥 한번 스스로 한번 실습을 해보면서 배우면서 뭔가 그 배운 것들을 한 줄 한 줄 남긴다 그런 의미로.
그 주석을 넣는 법이 우리가 어디 나왔어요?
주석을 넣는 법이요?
네.
그거가 이제 퍼센트를 아마 매트랩에서 퍼센트를 아마 넣는
퍼센트요?
네. 아니면 그거를 그냥 저쪽으로 그 워드나 뭐 아래 한글 쪽으로 갖고 와서요.
네.
거기서 그냥 주석을 달아도.
그냥 뭐 넣는 방법은 제 마음대로 퍼센트로 해도 되고.
네.
저기 그 오늘 배운 내용 복습하려면
네.
어디 부분을 봐야 되죠?
복습이요?
네.
복습은 요거 이게 내가 따로 올려둔 요 슬라이드를 보고요. 네. 요거는 그러니까 여기에는 안 나와 있어요. 책에는.
그런 것 같아서
네. 책에는 안
못
나와 있는데 이제 좀 되게 중요해서.
네.
그 강의 자료는 내가 요거는 올려놨어요, 그죠? 네.
그러니까 오늘 배운 게요.
네.
이제 리니어 시스템을 이제 원래는 저희가 리니어 커뮤니케이션 벡터이케이션으로 나타낼 수 배웠고
네.
오늘 한 거는 이제 이거를 매트릭스 이케이션으로 나타낼 수 있는데
네.
이거를 좀 일반화해서 행렬과 행렬 곱을 열이나 혹은 행관점에서의 이제 리니어 벡터이케이션 리니어 커뮤니케이션의 모임으로 생각할 수 있는 거고 또 뭐였더라? 잠깐만. 동시에 그 벡터이케이션을 이제 아니 벡터이케이션이래 행렬과 행렬 간의 곱을 이제 sum of the 랭크와 아웃터 프로덕트로도 생각할 수 있다. 이게 오늘 한 거인 거죠.
그렇죠.
이걸 확인하고 싶었어요.
네.
감사합니다.
네.
아까 그 추천 시스템 그거 설명하실 때 이거를 그러니까 아이템이랑 유저 통으로 돼 있는데 이거를 트랜스포트 해가지고 유저 아이템 이런 식으로 바꾼 이 과정이
요거로
무슨 과정 과정에서
이거는 그냥 그 편의상으로 나타내기만 이렇게 나타낸 거야. 그러니까 유저 바이 아이템이 아니라 아이템 바이 유저로 그냥 나타내면
그럼 그냥 이거로 굳이 바꾸는 의미가 그냥 편의성.
네, 편의성. 그러니까 우리가 그러니까 시작하는 매트릭스를 요 아이템 바이 유저의 매트릭스로 나타낼 수도 있고 존엄으로도 나타낼 수 있고 그런데 우리가 요거에서부터 시작을 하면 그래도 뭐 크게 문제는 없는 거니까.
그러면 굳이 바꿀 필요는 없다 이거.
근데 그냥 아까 뭔가 컬럼별로 컬럼별로 설명하는 것을 우리가 많이 다뤘으니까 그렇게 이해를 했으니까 그렇게 좀 이야기를 한 거예요.
감사합니다.
여기서 이게 RM 이게 뭐 어떤 걸 말하는 거예요?
그거요. 그거는 이게 매트릭스 사이즈가 이게 매트릭스가 이제 A가 이제 보통 n by n 매트릭스라고 할 때 그러니까 예를 들면 뭐 5 by 3 매트릭스예요. 그래서 이게 조금 또 길어서 이렇게 5 by 3 매트릭스 이게 이게 n이에요. 그러면 이거는 그 일단은 매트릭스 그러니까 ax equal b라는 꼴을 한번 써보면 다음 시간에 아마 조금 설명할 수 있을 것 같긴 한데 일단은 여기서 이제 x의 사이즈는 3개예요, 그죠? 여기 3줄 있으니까 3개의 리니어 커뮤니케이션 코에피션트가 필요하고 여기에 주어지는 b는 얼마일 것이냐? 이 m 디멘셔널 사이즈만큼이 주어져요. 그렇죠? 그러니까 여기가 보면 여기가 하나, 둘, 셋, 넷 이렇게 돼 있을 텐데 m도 혹은 여기 m이래. 여기 b가 벡터 b가 사이즈가 지금 요 m 하나, 둘, 셋, 넷 요 사이즈의 벡터로 주어지는 거죠. 그래서 A가 매트릭스가 m by n이면 당연히 매트릭스 이퀘이션인 AX equal B에서 B는 당연히 이제 5디멘셔널 벡터가 돼요.
아,
네, 그래서 이게 B가 이제 RM이 되는 거예요.
그럼 이게
차원만 그냥 나타낸 거예요.
로우의 개수를 나타내는 거예요.
그렇죠. 로우의 개수를 나타내는 거예요. 정확하게.
매트릭스가 벡터 값인가요, 그러면?
응?
매트릭스가 벡터 값이라고 생각해야 되나요?
매트릭스가 벡터 값이다?
그 벡터 계산은 스칼라로 하잖아요.
뭐 이렇게 하고
예,
이런 거요?
예.
네.
근데 그게 이렇게 돼 있으면은
네.
이게 하나 행렬인데
네.
그게 또 벡터라고 생각하는 건가요?
그렇죠. 예. 이게 벡터로 보면 그냥 그러니까 이게 벡터면 이걸 이렇게
네.
나타낼 수가 있고요.
네.
이거는 이제 원 디멘셔널 어레이라는 뜻이에요. 그러니까 우리가
네.
뭐 C나 이런 데서 이제 어레이 배열을 배울 때
네네.
1차원 배열, 2차원 배열 이런 게 있잖아요.
네.
그러니까 이거는 그냥 기본적으로 1차원 배열이라는 뜻이고요.
네.
이거 B가 이렇게 있으면
예.
B가 근데 그러니까 뭐 예를 들면 A가 이거를 이렇게도 쓸 수가 있어요. 어떻게도 쓸 수가 있냐면 B는 m by 1이라고 하는 2차원 배열은 배열인데 두 번째 이 차원이 그냥 1인 형태로 좀 우리가 생각을 할 수도 있어요.
네.
네. 그래서 이렇게 보면 이게 벡터를 그냥 2차원 배열이긴 한데 이 두 번째 차원으로는 이제 디멘전 값이 1인 거고.
네. 그러면 이게 만약에 그러면 이렇게 돼 있잖아요.
네.
하나 더 붙어 있으면은 그 5 곱하기 2 행렬이 답이 나오면
네.
그러니까 이게 R m 곱하기 2가 되면
그렇죠.
네.
근데 노테이션상 그때는 이제 소문자를 쓰지 않고 이 대문자에 이제 알파벳을 쓴다. 이게 이제 우리가 조금 매트릭스 나타낼 때 좀 약속을 하는 그런 거.
A 스팬은 무슨 뜻인가요?
이거는 A 스팬이 아니라 그게 이게 그러니까 A의 컬럼들을 모아서
네.
이거는 그러니까 이게 좀 말이 span of column of A. 그러니까 컬럼 A의 span이 M이랑 똑같다 이렇게 되는 거예요. 이게 이 말이에요. 그러니까 span이 그러니까 우리가 명사처럼 이렇게 좀 수학적인 정의로서 명사처럼 쓸 수도 있지만 span이 이제 동사여서 이렇게 쭉 이렇게 뭔가 다 도달한다. 그러니까 컬럼들의 리니어 컨비네이션들이 RM에 있는 모든 점들을 다 뒤덮는다.
리니어 컨비네이션들이.
네, 리니어 컨비네이션을 하면 이게 전체를 다 뒤덮는다라는 의미가 이게 span RM이 돼요.
그러니까 아까 그 리니어 그 컬럼으로 이렇게 해가지고 계산했던 그게 이 말인 거죠, 그러면?
네, 맞아요. 그 컬럼들의 이제 리니어 컨비네이션이 일단은 B가 주어지기 전에 일단 그때 지난 시간에 했던 것처럼 하여튼 컬럼들의 리니어 컨비네이션을 이렇게 자유롭게 해보면 그게 이제 우리의 전체 스페이스를 싹 다 뒤덮을 수 있으면 B가 어디 주어지든 그 스팬의 바깥으로 벗어날 수가 없고 그 경우 솔루션이 항상 존재한다라고 이야기를 했잖아요.
네네.
네, 그래서 이게 그 말이에요.
그냥 이거는 그냥 알고만 있으면 되는 건가요? 딱
이거요?
증명이 필요.
네, 증명은 증명은 그 하여튼 피벗 포지션이 그 각 로우마다 다 이렇게 A 파트에 있어야 된다. 그 변수에 해당하는 그 컬럼들에 다 있어야 된다.
네.
그거가 이제 여기서는 가장 중요한 점이고요.
이거 외적 설명하신 거 있잖아요.
네.
이거는 그러니까 이렇게 보통 행렬 계산할 때 이렇게 해가지고 이렇게 하잖아요.
네.
근데 그렇게 안 하고 그냥 이렇게 그러니까 컬럼으로 하고 이거 로우랑 컬럼이랑 다 곱해서 하나 행렬 만들고 이렇게 계산을 할 수 있다는 그런
그렇죠.
설명인 거죠.
네.
이게 근데 아까 뭐 머신러닝 뭐 이런 데 인용된다고 하셨잖아요.
네.
그게 뭐 그가 간략하게 뭐 어떻게 되는 건가요?
그게 그러니까 그 기본적으로 이제 그 랭크 원 아웃 오브 그러니까 어떤 매트릭스가 있을 때 어디 있었더라? 그 어떤 주어진 크다란 매트릭스가 있어요. 예를 들면 아까 영화에서도 보면 그런 유저 바이 아이템 형태의 매트릭스가 있다고 한다면 어디 있더라? 그거의 경우에 주어진 매트릭스, 크다란 매트릭스를
네.
주어진 커다란 매트릭스를 뭔가 랭크 온 아우터 프로덕트로 우리가 분해를 하는 거예요.
네.
그러니까 이게 좀 인수분해랑 좀 비슷해요. 그러니까 x제곱 마이너스 2x 마이너스 3이
네.
x 빼기 3 곱하기 x 플러스 1의 곱으로 나타내진다라는 거는
네.
그거 구하려면 조금 약간 생각을 우리가 해야 되잖아요. 인수분해라는 게 조금 어려운 문제잖아요.
네.
근데 x 마이너스 3 곱하기 x 플러스 1이라고 하는 곱은 우리가 쉽게 그냥 풀었을 수가 있죠. 전개는 쉬워요.
네.
근데 그거를 다시 팩토라이즈 하는 거는 좀 어려운 문제예요.
네.
근데 역시 마찬가지로 이게 이렇게 sum of outer product으로 이렇게 되어 있을 때 그거를 그냥 뭐 기계적으로 쭉쭉쭉 구해갖고 그냥 다 합쳐서 큰 매트릭스를 나타내는 건 어렵지 않아. 이게 전개에 해당하는 거고
네.
그 거꾸로의 과정은 훨씬 더 좀 어렵겠죠.
네.
그래서 이 거꾸로 뭔가 하는 게 좀 어려운데 근데 대신에 이걸 거꾸로 할 수 있으면 이제 아까 이야기했던 그런 레커멘더 시스템이라든가 어떤 여러 가지 애플리케이션들을 다양하게 활용을 할 수가 있어요.
그러니까 뭐 봤으면 뭐 1이고 안 봤으면 뭐
네, 뭐 그런 식으로 했을 때.
네, 알겠습니다.
네.
감사합니다.
네.
그 수업에서 트랜스포즈 설명할 때
네.
AX에 대해서 트랜스포즈를 취하잖아요. 그러면 X 트랜스포즈 A 트랜스포즈잖아요. 근데 트랜스포즈가 안 돼 있었던 거
맞아요. PPT 안 돼 있었다.
그래요?
더라고요.
어디에 있었어요? 그게?
이전에랑 뒤에 거랑 트랜스포즈를 한 걸 결과 같다고 이렇게 설명해 주실 때.
가만 있어 보자.
네.
내가 이 위-
트랜스포즈가 안 돼 있다.
요놈? 요놈인가요?
아니요, 그 수업 자료에서
수업 자료?
네.
여기 어디서?
이 다음
다음?
거였던 거.
네.
여기서 110 여기에 110 이렇게 돼 있잖아요.
네.
그런데 여기서도 110 이게 지금 뒤집혀야 되는데
그러네요.
네, 그래서 이거를 말씀드려야
그러네요.
되나 또 소리가 끊길 것 같아가지고.
아니 뭐 언제든지 이야기해 주세요. 이거. 네, 이야기해 주세요. 이거 좋은 지적이네요. 네. 트랜스포즈가 안 돼 있네.
네.
네. 알았어요. 내가 또 고쳐서 에러를 고쳐서 그거를 다시 할게요. 네.
그리고 혹시 저 청강인데
등록해 줄까요?
네.
네, 그 학번을 알려주면 내가
제가
해줄게요.
행방으로.
네, 생각으로.
네.
네.
감사합니다.
네, 그래요. 수고들 했어요. 네.
지금 가시나요?
나 뭐 챙겨서 좀, 뭐 먼저 가도 괜찮아요. 네, 그래요.
네, 고생하셨습니다.
네, 수고했어요.